Welcome to Calculus 2. In this lecture, we're going to introduce a way to find the area between two curves, or find the area of a region bounded by two curves. All right, so let's think back to your Calc 1 course when you were probably first introduced to definite integrals. You probably introduced that to tackle the problem of finding the area beneath the graph of a function over an interval a to b. This is a basic example. Notice the graph stays above the x-axis. Recall from Calc 1, if it dips below the x-axis, we have to introduce the concept of net signed area rather than geometric area. So we'll just stick with the basic interpretation here. The definite integral, basically area beneath the curve. Now at the time in Calc 1, the upper curve was curvy and the bottom was flat. What we're going to be looking at now in Calc 2 is going a little bit further, still dealing with finding area, but now the region is bounded between two curvy curves. We have a curvy curve on the top and then a curvy one on the bottom as well. Unlike in Calc 1, where the bottom, the x-axis, was flat, now here the bottom is curvy as well. All right, so how do we calculate the area here? Well, we should have the expectation, again, from coming from Calc 1 with the basic interpretation of definite integrals, that we should be able to evaluate this area by a definite integral. So we have at the bottom there, the area here in this case for our Calc 2 problem should be an integral from a to b, but of exactly what? What do we integrate? What's the function that we integrate with respect to x? We'll get to that, but at least from coming out of Calc 1, we have that expectation that there should be a formula for the area of this region in terms of the two curves, f of x and g of x. All right, let's go ahead and get to where this formula comes from. The formula that we're about to state, the area formula for the region between two curves, is rather simple. We could just state it, but for what we'll be getting to later in this course with other geometric quantities, volumes for certain solids, surface area, length of a curve, we're going to want to kind of have some foundation to build upon. So we'll try to do that here. The formula is rather simple, but we'll look at two ways to see it that will kind of put us on the path to understanding ideas later in this course. All right, so we're going to look at two different ways to arrive at this formula, or prove it, or derive it. The first is by taking the approach, let's start by finding an approximation of this area by using rectangles. Now, don't worry, we're not going to carry this out in detail, but we're just going to use this approach to give us some conceptual things to stand on and go forward on. All right, so you might recall from Calc 1, we split the area into a bunch of rectangles. They're going to have width delta x, and the key conceptual point is that the height of each rectangle, kind of fitting the rectangles beneath the graph of the function, the heights will vary. It is the function value that determines the height. You might recall using left and right endpoints of subintervals to do that. The basic idea here is that it is the function value, or y value, that determines the height of our rectangles. So we multiply the height by the width, f of x times delta x. That gives us the area of one rectangle. Now later in the course, we'll state this formally, but anytime you encounter integrals, what you're really doing, at least with definite integrals, is adding up small pieces. Think back to Calc 1 with area. Once you find the area formula for one of these approximating rectangles, f of x times delta x, you then add all them up. Adding or summing is integrating. So as soon as you get that area formula for one rectangle, it basically turns into that integral formula. Sums get replaced with the integral. The finite width, delta x, gets replaced with the infinitesimal width, dx. All right, let's try to do a similar approach here, but now our rectangles don't go from the curve down to the x-axis. They go from the top curve, y equals f of x, to the bottom curve, y equals g of x. Now, we're basically just going to subtract. In the sketch there, you can see the distance from the x-axis to the top curve is given by the function value f of x. The distance from the x-axis to the bottom curve, or the bottom of the rectangle, is g of x. If we subtract those values, we get the distance between those two curves. So the height of our rectangle is now f of x minus g of x. The width is still delta x. So we multiply, and here we have the area formula for a single approximating rectangle. We're pretty much done. We're going to conceptually add all these rectangular approximations up, and adding up turns to an integral, and the finite width delta x turns to the infinitesimal width dx. So we pretty much have it here. This transitions to this formula, this integral formula, and we get it. This is the area formula for the region bounded above by the graph of y equals f of x and below by the graph of y equals g of x over the interval a to b. Okay, now this is one way to arrive at this formula. This is going to be the approach that we use again when we start talking about volumes, surface area, and arc length, or length of a curve. Later, we'll be adding up small pieces, but the small pieces will be different geometric objects. All right, let's take a look at a second way to arrive at this formula. It's always good, in my opinion, within the calculus sequence and mathematics in general, to have several different ways to view the concepts. So let's take an approach using properties of integrals here and kind of building off of what we know. We can find the area beneath one curve down to the x-axis. We're going to use that idea here. So let's suppose we have this region, top curve y equals f of x, bottom curve y equals g of x. Now what we're going to do is basically think of kind of subtracting out two areas that will give us this. And if we look at the area beneath the graph of f, we have that bigger area. And if we subtract out from that the area beneath the graph of g of x, we get exactly the area of the region we're interested in, the area for the region bounded by those two curves. Now the benefit of doing it this way is now, since we have areas or regions beneath a single curve, y equals f or g of x, we can apply our fundamental idea. Each of these should be a definite integral. We have the first area on the right there as the definite integral from a to b of f of x. And then from that, we subtract the definite integral from a to b of g of x. If we apply properties of integrals, we can subtract those two integrals back as the single integral of the difference for the function f of x minus g of x. And notice that is the same formula that we arrived at a few minutes earlier. Different approach using properties of integrals versus approximation with rectangles from our first way that we saw that. All right, now this formula is perfectly fine as stated. It's a standard way to state this formula in terms of upper function f of x and lower function g of x. But personally, I don't like the notation because you have to keep in mind what f of x and g of x refer to. So let's kind of change that. Instead of writing it as f and g of x, let's kind of replace them with what they represent. F of x was the upper curve, g of x was the lower curve. Now here we're thinking of y as a function of x, so we can rewrite this formula as the integral from a to b of the upper function minus the lower function. But keep in mind here, we interpret y as a function of x. Okay, let's go ahead and take a look at some examples. Example 1 here is pretty straightforward. All the information is given to you. Pause the video and give this an attempt. This is probably about as simple as it gets for questions for this section. And then from the kind of following examples, we'll get to the difficulty will increase a little bit as we introduce other concepts. So pause the video and check in a few minutes. All right, hopefully made a good attempt at this. Now, one thing I want to point out is here, it's not referenced which is f of x and which function is g of x. So we're left with this question, which of these curves or functions is the upper, which is the lower function. Now, if you're able to graph this very quickly, then you can determine that just by your graphs, but maybe the functions are too complicated. Here's a nice little trick. You can pick an x value within the interval. Here the interval is 0 to 2, and we can plug that in. Whichever of those functions gives the bigger y or output value, that should be the upper function. Now this approach only works if the functions don't cross or intersect within that interval. We're going to see that in some following examples, but for this introductory example, that doesn't happen. So you can see here, if you plug in, we chose x equals 1, plug that into your two functions, and you get that the bigger y or function value comes from the curve y equals x squared plus 1. So y equals x squared plus 1 must be the function on top, the upper function, and then y equals negative 1/2 x plus 1 must be the lower function. This is, again, just a nice little tip to figure out which is the upper and lower function if it's not easy to graph. All right, this one is rather simple to graph. Basically just a straight line, slope negative 1/2, y-intercept 1, and then the other curve is a parabola shifted up 1 unit. All right, so your sketch would confirm what your upper and lower functions are. We pretty much have everything we need. We know which function's on top, we know which function is on bottom, and our basic formula says we integrate the upper function minus the lower function. Now be careful, anytime there's a formula with a minus, there's usually the possibility for sign errors. So a good tip I like to give is to use parentheses. It's arguably the biggest source of errors I see for students within the calc sequence. So in your formula, think of using parentheses around the y lower term or after the minus sign. That usually will clear up any possible errors. So if you do that here, and then be careful with the signs, notice the negative 1/2 x term from subtracting changes signs, and then the plus 1 subtracts out with the minus 1. So we're left with this slightly simpler integral from 0 to 2 of x squared plus 1/2 x. Integral is very simple. We just need to use the basic power rule to find the antiderivative. We apply that twice. And since it's a definite integral, we can plug in the limits 0 and 2, applying the fundamental theorem of calculus. All right, that should be pretty straightforward. You get here that the area between those two curves over the interval 0 to 2 is 11/3. All right, this example, again, is about as simple as it gets. You're given the two curves, you're given the interval, very minimal to determine which function is the upper and lower function. Now let's take a look at some other ideas that will be needed as we continue throughout the course. So I don't want to make examples harder just to make them harder, but the concepts will get harder, so let's head down that path. All right, so I want to point out here, we're going to transition, instead of having two curves given and an interval, so instead of a y equals f of x and y equals g of x being given over an interval a to b, we can have a region bounded just by two curves. So let's suppose the information is given, like in this example, where you just have the two functions bounding the region and no interval. So we are given the graphs of y equals square root of x and y equals x squared. Now, if this occurs, you're just given functions that bound the region. There must be intersection points. And if you do your quick basic sketch of the graph of square root of x and x squared, you see that they intersect in two spots. Now, in these questions, when you're not given the interval a to b that you're going to integrate over, we can typically solve for it by finding the points of intersection, where we basically set the one function f of x equal to the other one g of x. That's saying the points of intersection are going to be any points where the y values or function values are equal. And then we think of that as an equation that we can solve for x. So let's apply that here. Notice I didn't put any units on the x or y axis. That's intentional. So let's go ahead and make an attempt at finding the intersection points here. Pause the video, give this an attempt. I find even the best students in the calculus sequence, calculus 2 specifically, their algebra skills might be a little lacking. So pause the video, give this an attempt, see how you might solve this equation for x. You can see from your sketch that you should expect 2 different x values where these graphs intersect. We'll check in about a minute or so. All right, welcome back. So let's put the calculus on hold. We're just going to go through algebra, but as you might expect, algebra is a big part of solving calculus problems. And here there's 2 different ways that you can solve it. One approach, written on the left there, is to think of square root of x as a power, x to the 1/2 power, and then we can subtract that to the right side. And since we have 2 different powers of x, x squared and x to the 1/2, you can always factor out the smaller power. Now that first approach, kind of on the left there in the middle of the screen, that middle column of work, I find a lot of students in the calculus sequence have trouble manipulating expressions dealing with rational powers, like here, the 1/2 power. You can kind of still work with that with factoring. Notice in parentheses, you then have the remaining factor. Each power of x is reduced by 1/2. You have x to the 3/2, that's 2 minus 1/2, and then you have just -1. All right, now that point, you can set each factor to 0, and you'll get your 2 solutions, 0 and 1. Now, a perfectly good alternative approach, typically radicals might be a little tricky to deal with, much easier to work with positive integer exponents. Well, you might be thinking, well, if I square both sides of this equation, I can eliminate the radical. And this is, again, a completely valid approach. So instead of trying to subtract and factor initially, let's get rid of the square root of x by squaring both sides. On the left side, squaring a square root cancels out. Squaring x squared gives you x to the 4th. Now it's pretty much the same thing. We subtract and factor. Don't divide by x. You're going to miss a solution. Notice here, x equals 0 is a solution. If you were to divide the equation x equals x to the 4th by x, you could be dividing by 0, and that typically leads to missing one of the solutions. So never divide, always subtract and factor instead. And if you do that here, the factorization is much easier, dealing with factoring out x from x to the 4th minus x. And you still get the same 2 solutions, 0 and 1. So I realized coming into Calc 2, your algebra skills might have atrophied a little bit. Maybe your last mathematics course was more than a semester ago. But as we continue in the course, as you do more problems, those skills will kind of be built back up. All right. Recall the whole point of this. We're looking for the points of intersection. So for that graph we have sketched there, the points of intersection occur at x equals 0 and x equals 1. Now we can set up our area formula for the area of the region bounded by these 2 curves. It's going to be a definite integral from 0 to 1. And you can see from your sketch that square root of x is the upper function and x squared is the lower function. So we have the definite integral from 0 to 1 of square root of x minus x squared. At this point, pause the video, maybe give yourself a minute, see if you can complete the problem. This is a kind of a moderately more difficult example compared to example 1, since there was some work first in finding the points of intersection, which are our limits for the definite integral a to b, here 0 to 1. Pause the video, we'll check in a few minutes. All right, welcome back. Hopefully this one wasn't too bad. This one also can be integrated just by using the basic power rule. We're going to be using that a lot. So here's the power rule for antiderivatives. Rewrite square root of x as x to the 1/2, and you can apply the power rule to that as well as to finding the antiderivative for x squared. So add 1 to the exponent for each of them, divide by the new exponent. Notice for x to the 1/2, the antiderivative then contains x to the 3/2. We divide by 3/2, but notice I'm already kind of shortcutting it. Dividing by 3/2, same as multiplying by the reciprocal 2/3. So just be comfortable with that. And if you plug in your limits, the endpoints 0 and 1, using the fundamental theorem of calculus, you should get that this area comes out to 1/3. Okay, so that pretty much does it for a slightly kind of more complicated question. Still, we're given two curves, but no interval because they intersect. In this case, we have to solve for the points of intersection. In part 2, we're going to look at some of the more complicated examples dealing with more complex regions.